Hi there, and welcome back. So let's move to the next model. So in the previous video, we addressed the K-Omega. So one down, many more to go. So in this video, we're going to address the K-Omega SST. Okay. So remember, we're working in the K-Omega family of turbulence models, and what we have done or what we did in the previous tutorial pretty much will be the same. So since will be much easier in this video, we don't need to address too much theory. However, let's address the basic K-Omega SST model. So here I already have the links. So if you go to the NASA Turbulence Modeling Resources, okay, you have the links here. So in the previous video, we opened the Wilcox K-Omega. Okay, now we're going to move to the K-Omega SST, the ones proposed by Menter, and here you enter. You are going to find many versions of the model. So basically, the one that we're going to address is the first one. So as you read here, you can find equations, boundary conditions recommended by the author. So look at that. What we have in the estimate slice is recommended. Then like the wall, look at the dependence. D1 is the distance normal from the wall. At the wall, this model is Y plus insensitive with better properties, maybe, who knows, but usually better properties than the K-Omega 1988. Then I have some references here. So in this reference, okay, you have the link there. Yeah, you have the title here, and here also will give you the link, so you can find this one. This is a NASA technical server, and here you have some description of the model. So pretty much to the original paper where that was used to implement it. So here, interesting to comment about this model that they claim that they don't have the undesirable free string dependency. So usually these models, BSL model, the ones by Wilcox, they have this dependency. They're overly dependent in the inlet conditions. They or Menter claims that dependency has been removed, and with the same good properties of other models. In any case, here it's a nice reference. You can read, you can find the equations and so on. A little bit some comments in the descriptions. We go back here to boundary conditions recommended by the authors and so on. You have it here. Look at that. This model uses many support functions, damping functions, and so on. So everything is described here. What is interesting that I want to point out that this model, it is very similar to the K-Omega standard. So these are the equations, original equations. And let me go here to the original paper of the K-Omega, the one that we studied in the previous video. And the equation for omega, we have it somewhere here, okay? And this is the equation that for omega. In the new turbulence model, we have this for omega, and as you look at the equations, they are pretty much the same. The only difference is that we have this new extra term. So as you read in the paper, you will see that the reasoning for this term and legibly is that to avoid that dependency and so on in the free stream values that you have here. Another paper with some studies. But in any case, I don't want to go into detail. So now let's use my slides where I have a short review here of this model, and as usual here you have a short summary. I always give you the references, remember, it's very important. But the main takeaway here is that this model can be seen as a blended model between K-Omega Wilcox and K-Epsilon far from the wall. Far from the wall, this one, K-Omega close to the wall, this one, so it will inherit the good properties, and somehow you need to control that, using some blending functions and damping functions and so on. So this is what is done in this model, okay? In a few words, so it's much more than that. But okay, so we have our classical equations. So pretty much as you compare with the standard K-Omega, this will be an extra terms, then the coefficients that will change, but pretty much it's the same. But look at now how the turbulent viscosity is computed. So it's very different than the previous model. So now we have some other dependencies. Look at that. Now we have also vorticity in the equation. So somehow we're improving what we have now in comparison with the other models that we didn't have this vorticity and so on. So the blending function, how things work. So since here, mathematically speaking, gets very complex. But the idea of this function is just to control the behavior. So you have a function f1, so it is computing a value, so it's that value is 0, it will kind of will go to this behavior of k epsilon, and the value is 1, it will now go to this default to this value of k omega. So here you have how those functions control, change, and so on. As usual, you can compute for an omega epsilon, okay, like in previous one. And this model, one of the advantages that it performed very well in these situations. Now you have adverse pressure gradient, separated flows, and transonic shock wave, okay, tends to behave better than the K omega standard, okay. Boundary conditions, as I will talking now, so at the wall you can define it 0. Then omega usually is a large value, so there are a few differences here. You have the references, but it will be up to you. And that's it, okay? This is our brief description of the model. You have in the references in the video description, so I invite you always to read those references to get an idea. Hopefully we're addressing all those details here. So as usual, let me go here and okay, to the source code in OpenFOAM. And in OpenFOAM here, we're working with the K-Omega SST. And let's see if the authors, developers are giving us a reference. So actually, they're not giving any reference here. So specialization. So probably if we go to the SST base, we might find some reference. But look at that, they're not giving any reference. In the case, I already gave it to you. And let's see base here, K-Omega SST. Okay, so here you have the references. So all these papers that were used now, so it's up to you if you want to find these papers, get a better description. But in any case, we cover that briefly. So remember, these models are white plus insensitive, okay, and it behave better, or we're going to see maybe will behave better than the K-Omega SST. So as the previous case, we have everything here, high res, low res, so let's run everything. So nothing changed. So let me go to my terminal here, high res, okay, and let me launch run all. And look at that, you're computing all, like in the previous video now, case, computer all the quantities. But let's revisit here. So remember, these are your turbulence quantities. So we move from K omega, okay, 1988, and now we go to the K omega SST. Nothing changed. Everything that you see here is exactly the same. So look at that K, we have this value, okay, we're using, as we are using high res, we put the same value as the one that we put here, but you can put also 0. You have omega, okay, the value computed, look at that, we're using this value. As we mentioned, probably you can use something larger. It will be up to you to test it, okay, it will work. Then for nut, we put it like this, and it is up to you. So as usual, I like to go always from this for this one, but you can go for the Y star, Y plus, any of the other formulations. So basically the only thing that changed here was the choice of the turbulence model. We went here from the K omega to the K omega SST. In system also nothing changed, numeric is exactly the same. We're solving the exactly the same equations, just a few functions that change. Something that it changed also, let me open here control did. So remember, I like to use these cache temporary objects. So now these are different. So in the previous model was K omega, then here columns G, here is K omega SST. So when you're saving this one, be careful, you need to find the right model. So here, look at that, we have this one. So this is the distance Y wall, distance normal to the wall. So from this one, you can get that distance. So this is the square of that distance. Effective viscosity and saving here, that is the same as this one. So look at that, you have a lot of quantity that we're saving. Okay, we can use that for post-processing. And that's all, okay? So we have the solution here, and now let's move to the post-processing. Okay, so let me go here, build in, okay, and let's post-process. So as usual, we have the dictionaries there ready, the states ready. So we open this one, state 1. Okay, you need to change anything there. So already check and should work. It should be working. And in this case, we have wall function. So it's low res, high res, this model. a good result. Okay, look at that, a good match here, everything makes sense. Okay, and let's open another state. Okay, so let me go to state 2. Okay, so load here, paraView state 2. Okay, and we have already our script there with the post-processing, and look at that, everything makes sense here. We have been talking that node should pick somewhere in the boundary layer here, so where there, good results. This is our y plus, our shear stresses. Clearly you can see that everything is being modeled. And now let's go to the state 3, that probably from now on I will open this one, okay, because this is the one that we can use to validate, because we have the friction coefficient. Okay, so everything is okay. And I want to point out something that we're going, I think, yeah, we have that behavior there. So this looks okay. This is velocity profile, nothing against that. But now if we look at friction coefficient, look at this strange behavior here. These are our OpenFOAM results using the K-Omega SST. So see that it's going like this and then going out, and it's matching very well the turbulence results. So this might be telling you that this model kind of is catching here or detecting some transition to turbulence, and then is fitting the turbulence results. That might be an interpretation. I would say no, because transition to turbulence, you need verified meshes, and here we have a high ray and a wall modeling. So this is in my opinion, a more spurious behavior. And interestingly, let's compare, okay, with the K-Omega and see that. Let's see if we see some differences there. Okay, so let me go here, and will be this one. RANS, K-Omega, same result, and paraView open here. So very interesting result, because we have been saying, okay, we have the K-Omega SST, probably you use it a lot, you see in the literature that is the best model. But in this specific case that you have a wall modeling mesh in this geometry, look at that, kind of the old model, the K-Omega 1988, kind of seems that it behaved better here. Okay, so doesn't undershoot here. Okay, it fits here. Kind of probably overpredict here, but a small error, but it seems that it behaved better. So since that you have to take into consideration, not always is the best choice. Might be just a small error, okay? It's not something that it will say that the results are completely wrong, but look at that, you have some behavior there. So there you go. We have the solution with the high ray, a nice match there. And now let's move to the next case, and we can wrap up this video. Okay, so here again, nothing changed. Okay, so now before running, okay, and then getting the solution, remember that now we go to low ray. I haven't changed boundary conditions. Okay, exactly the same. It doesn't matter if you move from K-Omega 2006, K-Omega SST, or K-Omega SAS. Pretty much it's the same value. Probably one of the papers reference that you use will recommend you to use another numerical value, but it's pretty much the same. So here, look at the K remains the same. This one, it is the same. You go to Omega, pretty much the same, a high value, because we're following the recommendation from the author. And at this point, I recommend you, and probably in the 2006, we're going to do that experiments, use the wrong boundary conditions, and you're going to see the behavior, okay? Or try to do it. And then note, we have it here. And also you can do the experiments, choose any of these that are going to work well, or probably you can switch off everything and you're going to see some problems. Okay, so this is it. Okay, as you see, pretty much nothing changed, just in the name of the model, numerics remains the same. Something that I would like to stress also here, and I think I have mentioned that, but this is for new people that are starting to use these models. So to enable models at the wall functions, but just to stress, it's not only wall functions that you can model at the walls. There are many things that can be modeled, but as we're working with turbulence modeling, that's the model that we want to enable. Remembering this file boundary, you need to define a type of boundary condition. That type have to be wall, okay? Be careful. If you put patch, you are not going to enable these wall functions, So be very careful. Active walls where you know that you want to apply wall functions. In this file here in constant polymesh boundary, put it as a wall. Okay, be careful about that. So at this point, I can close there. I think I have nothing else, nothing to mention. And actually, I don't need to run this case because we have the solution there. So let's go and, okay, I know I was looking to another folder probably. Okay, to the KO. So I was in the wrong folder, should be this one. Okay, so I have to run it, but nothing changed. To remind you also, we have this Python, so you run the Python script and I will do the post-processing without going through the paraView stuff. So let's go and let's run here, run all. Okay, so let me run everything and see you in a while after we have the solution. So we're back. We have a solution. So also here when running, I plot the residuals. I like to use Python, so you can install Python, or you can use the function again, OpenFOAM, if I myself know that it's faster with Python. I also have my own script, but well, I don't want to use that one. As I say in Python, I try to overcomplicate things. But something interesting here is to look at the residuals, and I want to point out that the residuals are not indication that the solution is correct or you have convergence. Okay, be careful about that because they can be misleading. We talk about this a lot about this when we do a finite volume course lectures. So the fact that these residuals they are not going down in a monotonic way doesn't mean that the solution is divergent. Can be many reasons, can be numerical reasons, can be the slope limiter, or also can be that you have some unsteadiness in your solution. Can be many factors, but it's not an indication that the solution is wrong or divergent. In this case, what we see also is initial residuals, but always your residuals are going to reach the final tolerance. See here, final tolerance. Okay, but this is your initial residual, so be advised with this one now that this is not an indication that the results are wrong, and this is very good. Look at that K and omega converging very well. Then velocity, U, Y have some issues there, or not issues, it's not going down in a monotonic way. For me, it's not a problem. I'm quite sure that you play with the numerics and you choose a different slope limiter. This can improve, but in any case, it's not a big deal. Okay, don't worry about that. So here we have all the post-processing. You can revisit now everything, your output and so on. So also you can look at between solutions and compute. You look at the y plus values. Obviously you will see that they are slightly different, different equations and so on, but everything converge since that it converge, right? So now let's do the post-processing. paraView built-in. And let me open this state 1. Okay, so remember, now we are wall resolving. And recall that in the previous case, we had an strange behavior with the wall function. So let's see if we have it in this case as well, was the wall shear. But if we compare wall solutions, look at that, it's perfect. Okay, what we know about theory, everything makes sense. Okay, so nothing wrong about this. So it's computing here, doing the blending, then the mashing here, you have your shear stresses there. So let's move then to the other state in paraFOAM. So let me go here, load state paraFOAM, open this one, and let me bring back this paper, the original paper, now the one for the Wilcox model. And just to show you that this is a very nice paper, I invite you to read it. But look at that, what I'm talking about, the ways to validate, and look at this plot. This is production and dissipation. So you can take a look, and here they make that discussion that they are imbalanced, then why we have this behavior here, what is happening, what is equilibrium, and so on. So look at that, they show that plot as well there. Very important plot for me. Okay, it tells me a lot. And look at here that we have production and dissipation. Okay, everything in equilibrium here, the behavior here, then we have the peak somewhere in the buffer layer, then the no comparison with the shear stresses, then remember that the peak in K not necessarily corresponds to this peak. So look at that, similar scales, but they don't correspond there. But everything makes absolute sense for me. So a way to validate just based in what we know about turbulence without looking at any experimental result. Okay, so I can say that my solution is okay based on that. And finally, we can take a look at a physical value, you know, just to be absolutely sure. So, okay, low state. Okay, I think override that. Let me go. Okay, so let me go. I think I have a backup here, and let me take that backup. Paraview here. Bam, 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 bam. So be careful. Sometimes happens that you choose the wrong option and you can override. So I think that one should do the trick. And let me go low state, paraView, state 3, okay. And there you go. So we have this one, and to compare with not this one, I need to compare with the high red, paraView, high red. And look at that. In this one, we were getting this strange behavior that we didn't have with the K-Omega. Then we're going to do the K-Omega SST, the K-Omega 2006. Are we going to have this? Yes or no? And let's see. But look at that, a very good match. Everything makes sense. So it seems that this specific model, in this specific case, for this specific numerics and combinations of boundary conditions, since that low red works better than the high red, just based on the friction coefficient. Based on everything else, it is okay. I don't see anything. I cannot criticize that. So there you go. How to set up now the K-Omega SST, some comments about numerics, boundary conditions, and so on. And to remind you that you have the folder. In the folder, you have RANS, RANS. So by the way, RANS is exactly the same setup, but you need to enable time. So we're not going to do everything. I'm going to pick those two cases, probably K-Omega, 1 K-Omega, 1 K-Epsilon, and spiral matters. That's all. Then we have to scale and resolve it. Then, well, you enter here and you choose your case, and we were working here in K-Omega SST, and you have everything. So to summarize here, okay, and let me cross this model here. So now we have this one, and we're going to keep now dropping models here. So fantastic model. Always read your documentation. You have your references there. Get used to the models. You have your recipe. Want to stress that this recipe that we're giving here, now boundary conditions and numerics, it doesn't change with the geometry. Okay, you only need to change the name of the patches, and probably numerical values, but you can safely use. So with this, we're done with the K-Omega SST, and see you in the next video. That will be the K-Omega 2006, my favorite model of the K-Omega family. So thank you. See you next time. Bye.